Hello everybody. In this video, I will show how to analyze a Gable frame using Staad Pro. The problem I have considered is the Gable frame. You can see here the column height of the column is 4 meters, 4 meters. And the Gable, the inclined members are between 2 and 3 and 3 and 4 you have inclined members, which is at a height of the crown height is 1.5 meters. And you can see here there is a UDL acting outward, and also here a UDL acting outward, or I can say that this UDL is acting in the negative direction of global x-axis, and this UDL is acting in the positive direction of global x-axis. Okay, and you have here a member, a horizontal member or a cantilever beam, I can say. This is the width is 0.75 meters or the length. Here also the length is 0.75 meters. Here I have taken a point load of 20 kilonewton and a point load of 10 kilonewton here. This will simulate the effect of the Gable, the corbel on the columns. You can assume that this is a corbel and this is a corbel. Here you have crane loading induced due to lifting of the materials in the industrial shed by the cranes. When the hook of the crane or the chain of the crane is towards this corbel, you have larger axial load induced by the load that is lifted by the hook, this side, and you have the other side the lesser load. So this is how what as a practical case I have taken this, and this I can model this as a cantilever beam in Staad and apply this load, but normally it will not be done like that, because this cantilever member will not behave like a corbel, because usually corbel we design using the strut and tie model. We doesn't design like a cantilever beam. Anyhow, that is the case. For that, what we do instead, we will convert this load into an axial load, and a moment. See this, if you add the equal and opposite loading here of 20 kilonewtons, one is downward and one is upward, then this load and the upward load and this separated by certain distance will form a couple. That couple will be usually expressed in terms of moment, and that moment is a clockwise moment about this point, right? So therefore it has become a clockwise moment. We should apply it as a clockwise moment of 15 kilonewton meter. How this is 15 kilonewton meter? This is 20 into 0.75 will be 15 kilonewton meter, as well as you will have this load which is 20 kilonewtons. Similarly, this side also you will apply an equal and opposite load. This load and this load will form. Here you should apply. Here you should apply the upward and downward load, right? And this load and this upward load will form a couple which is in the anti-clockwise direction, and you will have the load which is acting downward. That you can see here. The 10 kilonewton is acting downward, and this will form a anti-clockwise moment. The couple will be expressed in terms of moment, and it is a anti-clockwise moment because force into perpendicular distance about this point, the moment is anti-clockwise, correct? And that moment we have expressed here, which is 10 into 0.75, which will be 7.5 kilonewton meter, right? So at this joint you will have 20 the axial load as well as the moment. Here also axial load as well as the moment. This point is at a distance of 3 meters. See this this loading will be acting From joint 1, it is acting at a distance of 3 meter. Whereas when you come to this column, you should consider the starting node is this one. From this fourth node or fourth joint, the load is acting at a distance of 1 meters. 1 meters. While giving the input in the Staad Pro, you should consider the starting point for the first beam as 1. So hence the distance is 3 meter. And for the last column, or the second column, the starting distance is point is 4. And the distance you should take it as where the point load and the moment is acting, the distance you should take it as 1 meter. 1 meter. That is about the columns. Coming to the inclined beams, you have a 5 kilonewton load, 5 kilonewton, 3 loads are given. One is at the starting, middle, and the end. And here also this side, starting, middle, and the end. Okay, since these members are inclined, as we saw in the previous problems, that for any inclined member, you should consider the local coordinate system rather than the global coordinate system. And the local x-axis will be always along the member axis. Therefore, member axis for this member is x-axis, and the perpendicular will become y-axis. And for this member, this is x-axis, positive x-axis, and this becomes positive y-axis. Positive y-axis. Okay, that we should understand. So this let us go to the Staad Pro and let us see how to analyze this type of Gable frames. This is a typical problem of the industrial frame. The industrial frame, typical problem of industrial frame. This problem can be dealt as the forces that occurs on the members due to suction pressure, which is exerted by the wind load. Okay, and you can see the supports are the hinged supports. Normally, in a industrial shed, we give hinged support so as to avoid larger moments that are generated and which will contribute for larger size of the foundation or the footing. So you can provide fixed support also, but it will generate a lot of moments, and therefore the footing size and the pedestal size will be huge. To avoid that, we normally resort to the pinned or hinged supports. A typical practical case I am talking about. So let's see how we can solve this using the Staad Pro. Also, you can see one thing that this frame, for example, this column and this beam is a mirror image, or this beam and this column is a mirror image of these two beams. This is a the symmetry. The problem is a symmetry case. So these two are the mirror image of these two. Right? Let's see how to deal with this problem using Staad Pro. Let's go to Staad Pro as usual. Go to new project, plane frame. This is problem number 7. Plane problem 7. Next. Plane problem 7. Next. Finish. So first joint is 0, 0, and the second node was at 4 meters, 0, 4 meters. It is 0, 4 is the y distance, right? And the crown, which is the node 3 was at a distance of, the coordinate of that is 4, 6.5. 4, 4 is x-axis, and this is 6.5. I got the 3 nodes. 3 nodes. Now what I will do, I will just connect them like this. And just connect them like this. Now the other side is the mirror image of this, correct? So how to mirror this? How to mirror this the left hand part? You see here we have one command here, generate mirror. Generate mirror whenever you want to mirror a frame which is symmetric, then you can go to the generate mirror. So what you can see, observe how to deal with this is you should observe here. You have a small two-story frame here, two-story frame, and this frame you want a mirror image, a mirror image. So how will you get a mirror image? Assume that this is x-axis and the vertical is y-axis here of this frame. You should place a mirror in between or by the side. You should place a mirror so that you get the mirror image of this on the other side. Or inside the mirror you can see the mirror image, the image of this. Is it not? You can see this line here inside the mirror. The first column you can see here, the last column you can see here. So to generate the mirror, you need to place a mirror in between. If this is y-axis and x-axis, where you should place the mirror? You should place the mirror in y-axis and z-axis, or I can say yz-axis, so that you get here, right? So in our case, now suppose if this is z y-axis, then where will you place the mirror? Mirror you should place in y-x-axis. Y-x-axis means to say here you should provide those details. Mirror plane. If this is y-x-axis or xy-axis, then you should keep the plane of the mirror in the yz-axis. Then you should give yz-axis here. If this is z-axis, if this itself is yz-axis, then where you will provide the mirror? You will provide the mirror in y-x-axis. Then only you will get the mirror image. Is it not? Then you should give here xy-axis, xy plane, right? Xy plane. So let's see now. Well, in our case, how to deal with this. See, this is the members. You can find these members which is in the xy plane. This is x and this is y plane. As you can see here, z is perpendicular plane. Okay, so this is xy plane. Now to create the mirror, where I should mirror image, where I should place the mirror? I should place the mirror here. I should place the mirror here so that I get the mirror image of this. Correct? Which is this? Which axis is this? This axis is y vertical, and you should you should place the mirror. The other axis will be perpendicular to this plane, perpendicular to this xy plane, which is y z axis. Correct? So you should choose here yz axis. Generate the mirror in yz axis. Okay, if you do that, and you should take the position or the point where at which point you want the mirror. Okay, so for that you should take this, and you can choose which point. This is the point of symmetry, so I will choose this point, and you okay. Select the members it is asking, and I have not selected the members. So what I will do, I will select the members first. Control. Yeah, you can control this. You can select this member. To choose another member, you can take control. You can press control and then drag this. So both are highlighted or selected. Now you go to generate mirror. As we know, it is YZ axis. Take the point. Then where you want the mirror image. Okay. Now you get the mirror image of this side. Hope you have understood. This is XY plane. You have to place the mirror in the YZ plane so that you get the mirror image in the other side. Okay, so this is the frame which we wanted. We will now move on to the supports. We want the pinned or hinged supports, and then go to the select the nodes where you want to assign them, assign to the selected nodes. Next we move on to the loading, both case add primary none, as we will be loading or anything you want to do, close, loading, add. See, now this side you had a load of 5 kilonewtons as well as this side, is it not? Let's directly go to member load, uniform force, you have a 5 kilonewton load, and you know that the horizontal direction, it is acting in the negative direction of horizontal. If you remember the problem, it is acting in the negative direction of global x-axis. Globe x is positive in this direction, but here the force was acting in the negative direction. Therefore, I will take minus 5 in the global x direction. Therefore, add. Okay, add, and to this side it is plus 5 because this was acting along the positive x-axis, correct? So therefore, it is global positive x direction, and it is positive. Add. Okay. Then I have here a point load which was at 3 meters and a moment there itself. Let me go to concentrated force. See, this is the node number 1, and this is node number 2. So therefore, this is the starting point. From here, the load was acting at a point of 3 meters. Therefore, I will take minus 20 was the load, which is acting downward. Hence, it is minus 20. In which direction? It is global y direction, correct? At what distance from the starting point? 3 meters from the starting point. The starting node is 1. Okay, so add this, right? So next, I will come to this side. See, this is node number 5, and this is node number 4. You can see when we mirrored it, the node numbering has changed. It is not as per our diagram, is it not? You can see here the node number is 3 here. This node has become node number 5. This node has become node number 4. If we would have taken the nodes by ourselves, what we would have done, I would have copied this first and placed it here, so that this would have become node number 4 and this would have become node number 5. Anyhow, we have, after mirroring, we have got node number 4. That is why I am checking the nodes because there will be changes. Okay, this is node number 4 and this is node number 5. Okay, so therefore, this is the starting point, and where we have the load here at 3 meters, which is 10 kilonewtons, See, distance d1 I should take now as 3 meters, But while explaining, if this node was were to be 4th node, then I should have taken it as 1 meters. Anyhow, we have got this as the 4th node. From here it is 3 meters, right? That is global y direction. I will add this. Add. Okay. Next, we will move on to concentrated moment. This moment, clockwise direction, acting at a distance of 3 meters from the node number 1. Correct. So clockwise means in Staad it is negative, minus. What was the value? The value was 15 kilonewton meter, minus 15 kilonewton meter. D1 is the distance of the moment from the starting node. So what is the distance? Here, from here it is again 3 meters. Let us take 3 meters, and moment will always be acting about global z-axis. Global z-axis, add. Okay, and this side we have plus value plus 7.5, which is anti-clockwise, since it is positive. And since the node is 4 here and the node is 5 here, the starting node is 4 again. So it is at a distance of 3 meters. The moment is acting. I will hold on this 3 meters as it is. Add. Okay, that I have done. Let me first assign these things. Then I will come to the incline members. Close. This is for the first member assigned to the selected beam. And now this is the negative direction of global x-axis, right? And this is the other direction, in the opposite direction. And we will take the concentrated force which is acting on this beam is at 8.3 meters. This is the concentrated force. And here the member is acting at a concentrated load of 10 kilonewtons at 3 meters from here. Next we will go to the moments on this member. It is acting at to be selected. It has assigned. I think the scale is very less, so that is why we are unable to see here. Okay, come to this one, then choose this member and assign here also. Okay. We are unable to see that moment. We shall increase the scale of the point moment. Maybe in 0.01 if we give apply. I think it has increased. I will give it as 10. Now you can see. I have changed the scale of the force. The moment. Now you can see this is global Z. I will just reduce some more or increase some more so that I get a clear picture of that. Instead of 10, I will keep it as 25. See, these two I am getting here. Okay, this is clockwise 15 kilonewton meter, and this is anti-clockwise, which is same. So we have completed now the forces on the columns. Let's move on to beam. Again, we'll go to the loading, go to load. Now you have loads at 3 different points. One is at point 1 or node 2 and node 3, and in between the node. I think it is at the midpoint. Okay. Now how to consider the starting point and the end point? The loading again, go to member load, concentrated force. This is 5 kilonewtons in the positive local y-axis. In the positive local y-axis, correct? So therefore, this is positive local y-axis. I will just add it. I will just add that. Then at the end, I should provide another 5 kilonewtons, here in the global y-axis direction, positive global y-axis direction. Let us see where it is. What is this length? If I double click on this, the length is 4.71. I will consider 4.716. Okay, 4.716. It is 4.716. 4.716. That is also local positive y direction. Add, and the midpoint. Midpoint. What is the midpoint of 4.716? It is 2.358. So I will provide here 2.358. Okay. Add. Close this. Here now. The first point, I will just select this number, assign to the selected names. So this is the midpoint one. Now I should give a 0. Change this. Close. So this is the first point, and we'll assign this now. This is the last point. For the midpoint, even if you don't give anything also, if you leave it as it is, you will get the midpoint. You will automatically the load will be assigned to the midpoint itself. This is how the load is being assigned. Load is being assigned. This is local y-axis. Local y-axis, local y-axis. And this side also you have the same load. What I will do, since the load is the same, the starting point, the first load, whatever I have taken, the positive y-axis, this is also positive. Now here the loading is also in the positive local y direction. We will go to the end node, assign to this B, and here this is the midpoint. Now all the loads have been assigned. Load have been assigned. You should note that this is local forces. You should apply only in the local direction. Okay, and you should know which is the local positive directions. Positive directions. Now we have applied all the load, and let us provide the properties. The columns, I think it is 2i or nothing we have given. Let us consider all as I value. Define general. This is 0.000045. Add, close, provide all the members with the I value, then remaining is value. Comments, analysis, perform analysis, okay, analyze, run analysis. Okay. You can first check the deflection diagram, how it looks. You just see. This is the deflection diagram. See, though you have hinge support here, the lateral displacement is 55 mm. X value 55 mm here. X value is 55 mm, the lateral displacement. Because of the frame rigidity, though here you have hinge support, this will not tilt fully. Also, if you have the loading, they are equal and opposite to each other. In the left hand side part and the right hand side part, they are equal and opposite. And but due to that loading, you have a vertical deflection as well as the horizontal deflection. Okay, this is the deflection diagram. We close this. Let's see how the bending moment diagram looks. Diagram. We will just control and scroll the mouse button. You can see this is the bending moment diagram. And here there is a sharp change here in the bending moment diagram due to the application of the moment. See, where you have concentrated moment, there will be sudden change in the bending moments values. Is it not? So that is why there is a sudden change here and here. Okay, and this is the remaining bending moment diagram of the inclined members. This is the bending moment diagram, and you can check the shear force using control. Scroll the mouse button. You will get the shear force diagram. Shear force diagram. Also, you can get the axial force diagram. This is the axial force diagram. Okay, axial force diagram. And as usual, you can go to post processing. Okay, and you can get the values of bending moments. Go to result, view value, view. You can select whichever you want here itself. You can also select axial, annotate, close. And this is the bending moment values. Here are the bending moment values. Now switch it off and go to shear force. These are the shear force values, and take the axial forces. Axial forces. This is how you have to solve a problem on the Gable frames. Gable frames, very important. All your industrial sheds will be analyzed like this. Only the member properties, by selecting the member properties, you should select the tapered sections. Tapered sections, because tapered sections are more economical. And earlier, all the industrial sheds, we used to go for the trusses, but nowadays it is PEB structures. For PEB structures, this is how we have to do. Only the loading on the inclined members you should change, because there will not be point loads. It will be UDL only. We will convert everything to UDL only. Then converting back to UDL. Other than that, everything is same. And this is how you can easily analyze the industrial sheds. That's all in this video. Thank you.